Ngalakin Khadijan Nyunga Boja.
Okay, welcome to part 2 of the Laplace transform. Up till now, we've discussed the background of the Laplace transform, how it's defined, and how you try to calculate it, the poles and zeros, the fact that it's got different regions of convergence, and the various properties. However, we need to still look at how you calculate the Laplace transform. Do you really need to go through and work out that integral expression that you've seen? We did do that for a simple function, which is the exponential function, but how about other functions that we will encounter? Do you still need to calculate the Laplace transform directly? The answer is not really, because we have tables which will give you the answer directly. More importantly, we also have a table of the properties of the Laplace transform. Without the properties, the Laplace transform is pretty useless, but the properties will make it very, very useful, and the whole reason why we have the Laplace transform in the first place. So let's see what we're talking about. Let me share my screen. So let's look at the table of what we call Laplace transform pairs. Now, this table exists in various textbooks, and if you have a handbook, an engineer's handbook of tables of everything, you'll probably find a table of Laplace transforms. And you can even Google tables on the web. They come in different forms. Some tables have a lot of Laplace transform pairs, some have less. And the columns could mean different things. Now, the table I've shown here comes from one of the textbooks. It contains these entries here, and there's another table connected to it. So let's describe what typically you will see in most tables of the Laplace transform. So what you see here is the signal function, the function of time. What you see here is the transform of that signal functions. So for example, the one that we looked at was this signal, if you remember from the previous part 1. And indeed, we did work out that it was 1 over s plus a. And usually we'll also have a statement of the region of convergence, the values of s for which the Laplace transform of this exists and is equal to that. Other signal functions that we commonly use is a unit step. We define that. Unit step has a very simple transform, 1 over s. Region of convergence is all positive values of s, or positive real parts. The ramp, this is known as the ramp function. We haven't really defined it, but that's what it is. It's 1 over s squared. We have the unit, this is interesting, this is the unit impulse function, delayed by tau, and it has a transform of e to the minus s tau. And it's defined for all s. Of course, if tau is equal to 0, which it can be, in other words, if tau is equal to 0, it would simply be our, yes, my pen is acting strange. Apologies. That's it. So that's if tau is equal to 0. And if that's the case, this would just equal, I think, 1. Sometimes my pen has issues on this laptop, so I apologize, but people say I usually speak quickly, so when I do that, that's time for you to reflect for a couple of seconds that I go quiet as I try to figure out why my pen is not responding. Okay, this one we've seen. Oops, let me go back to my spotlight. We've seen already. This one you may find where you have a t in front. That one is just 1 over s plus a squared. The remaining ones here we rarely see, though they appear in different forms, so it depends on the question. What is interesting here, cos and sine, which are very popular functions, of course, we defined these in chapter 1, and sinusoidal functions are very important. You will notice that these only exist for positive time. And these are the Laplace transform respectively. I pose it to you whether there is a Laplace transform for cos omega 1t for all time t, both positive time and negative time. I used to have the answer, I don't recall. I'll leave it for you as something to explore. But in the tables, you'll usually see it with the unit step effect. Now, these are all functions that exist for positive time. You also have functions that exist for negative time. So we throw in the unit step for negative t. For example, the one we also looked at was the exponential function that only exists for negative time. It's still 1 over s plus a, but the region of convergence is flipped. The same thing if the unit step goes in the opposite direction. Same transform, but the region of convergence is also flipped. And you can check whether that's the case for this one too. Okay, here's some common ones that we see. The unit impulse response, indeed, it's equal to 1, as just stated. The step is 1 over s. In this case, this is an example of where you can actually work out what the unit step is. That's even easier than the exponential function. If you have a unit step, that's integral becomes that, because the unit step is only defined for positive t, and it's defined as 1. And that can easily be seen to be equal to 1 over s. I think that's easy to see. I leave it for you to calculate indeed whether 1 over s is the answer. It should be. Don't forget, when you see infinity, you've got to take limits. So try to see if you can carry out this integration and whether it's easy or hard to do. But something, every now and then you should try this to test yourself. These things which should be easy to do. So try it. Now the properties. Now these are really, really important. And there are two very important properties which effectively confirm the part of the Laplace transform that Pierre-Simon Laplace actually invented it for, which was to easily solve differential equations. And we'll see the two properties in this table, and I'll emphasize them afterwards. So what is a table of transform properties? This is a bit unusual, but it's quite common with transforms that not only do you have pairs, look up a table where you can look up the transform values, but you also have properties. So the first property is that the Laplace transform is linear, which is a good thing. It makes it easy to calculate the Laplace transform for a whole combination of functions, which are linear combinations of, say, x and y. It's simply a linear combination of the respective transforms of x and y. You have the time shift property. So if you take a single function and shift it by tau, apparently the Fourier transform is a Fourier transform of x of t, which is what that is. Notice that's how it's defined here. Xs is x of t, with a pre-exponential here, e to the minus s tau. So the delay throws in this prefix, this extra function. Now you'll notice I'm looking from this column to that column. This column here, the unilateral transform, let me bring in the rest of this here so I can do this to it. Yes, that's what I did. I did actually put an X. The reason is, as I said right at the beginning, we will only be looking at the bilateral Laplace transform. We will only come back to the unilateral transform right at the very end when we actually look at circuit analysis, complete circuit analysis. One of the reasons why I avoid the unilateral Laplace transform is things like, you probably see this here, if you look at the shift function, which is simpler for you to understand, this one or this one? I put my hands up for this one. This is the same form, but it seems to have this qualifier down here that you have to sort of process and understand if it means anything. Here it's quite clear. It's just that, simple, all cases. The other column we ignore is the regional convergence. It is important, but by this stage, we've probably accepted that the regional convergence will always be for right-sided causal signals. So the uniqueness aspect of it is not an issue because, as we discussed, region of convergence is important to determine the unique mapping from the Laplace back to the time domain. So in most cases, we won't need to look at the region of convergence unless it's to tell us whether something funny happens in terms of having a region of convergence. In most of these cases, it's either dependent on the region of convergence of the original x or y in some standard fashion. And sometimes when you see an expression like that, you've got to actually figure out what does that mean. most of these things, sometimes they're just stated and you sort of park this and you only come back to it when you need to know, pretty much a need to know basis. It's unfortunate. There is information here which you don't have to know 100%. Some of the stuff that we do cover and include could be a bit superfluous. You can't avoid that, because if you only include the information you need to know, there's a lot of things you still need to know, and it's always good to have complete tables rather than partial tables. So this is pretty complete. We even have the unilateral transform, which at the moment we are ignoring anyway. Okay, you may have a case where you multiply x of t by an exponential function, and that gives us this interesting effect where it's the Laplace transform shifted by s. You'll notice something unusual, and this is not something we highlight for the Laplace, but I'll tell you this, it's something we will highlight when we get to the Fourier transform in the second half of the unit. And that is that here you have a shift in time, here you have a shift in s, here you have an exponential, here you have an exponential. It seems there's some sort of mirror or duality taking place. Sometimes you see that, and the reason is if you go back to the pair. Oh, this is what happens. Get rid of that. I want to go back to this table also for another reason. I did forget to mention when we go back to this table that these Laplace transforms work both ways. If you're given a function of time, it'll take the Laplace transform. Conversely, if you're given the Laplace transform and you want to know what the function of time is, you go back here. And if you're given the regional convergence, you can pick the right form that you go back to. So these go both ways, from t to s and from s back to t. The other thing I didn't mention is you see this funny expression. This is what you need to do to actually take a Laplace transform and go back to the time domain. As we will see, you don't use this expression. We do use this, however, and we have defined this as the Laplace transform of t. Now, I sort of forgot what I was trying to see here. So let's go back to the original question. So continuing on. So here you have the scale version. So if you have a scale, you also scale the Laplace transform in the opposite direction. Instead of here you multiply by here you divide by as, and you also have a scale factor on the outside. If you convolve two time functions, you multiply in the s domain. Little light bulb lights up, and this is one of the first light bulbs. If you multiply, if you have this effect, it's a bit unusual. You actually have to take the derivative in the s domain. If you take the derivative of the time function, it's actually s times in the s domain. Light bulb number 2 is lighting up now. Finally, if you integrate the function, you divide by s. Now, what are those light bulbs I was trying to tell you about? Here we go. Convolution. Convolution in the time domain becomes multiplication in the s domain. Do we care? Go back to the first half. We care a lot, because for the zero state response, if you remember, we had to take the convolution of the input with the impulse response, and a convolution is difficult to calculate. Believe me, it's only for simple functions you can calculate the convolution. But if you convert x to the s domain, if you convert y to the s domain, then the Laplace transform of the convolution is just a multiplication in the s domain. So then, if you can go back to the time domain, we would have carried out the convolution with no convolution at all. In fact, the way you would do it in the simplest case is you use your lookup table, look up the Laplace transform of x, look up the Laplace transform of y, multiply in the s domain. Multiplication is easy. And then if you have a big enough table, you may find the Laplace transform of the multiplied product, and they will give you the final t function, which is in fact going to be the convolution of x and y. In other words, you don't do any convolution. You do multiplication. That is very easy, very simple. That in itself is powerful. But that's not the end of it. Remember this property. Now, in the table, we had it like that. You can generalize it to this form. For the second, third, and fourth order derivative of x, you simply take s and raise it to the power of n for the nth order derivative. Differential equations. Remember those differential equations, which were our derivative, the first derivative, the second derivative, the third derivative of x, and ditto for y. Well, if you take Laplace transform of a differential equation, and don't forget, Laplace transform will base the property of linearity, then what you end up having is s to the x, s squared to the x, s 3 to the x, etc. You convert your differential equation to a polynomial equation in s. Polynomial equations are a lot easier to handle than differential equations. Wow. Get rid of convolution, get rid of differential equations. You're indeed doing more, you're doing less calculus being especially differentiation integration, which is what convolution involves, to algebra, which is polynomials and multiplication. That was the reason why Laplace invented the Laplace transform, and this is why. But as we will see, it does a lot more than just this. And what I've thrown in the notes for the curious is how you actually derive this property. The textbooks actually derive each of the properties. I've avoided doing that here because that's just technique. But in case you're wondering where these properties came from, it's good practice to know how you would work out these properties. In case you want to create a new property that you don't see in the table, you say, hey, this property doesn't exist. I want to add this as an extra row in the table of properties. So in this case, what you would do is you would take the Laplace transform of that using the integral expression for the Laplace transform. That's what it is. Then you use integration by parts, yes, because you've got two functions here. And integration by parts is handy when you have a derivative of one of these functions. And you can show that this goes to 0. I have to think about that. I'll get you to think about it as well. But this is the interesting one. You end up with that. And that integral is x of s. So lo and behold, sxs. And you can show the same thing when you look at the nth derivative. So let's now look at how you put it all together, pairs and properties, how you combine them. The reason is that by combining pairs and properties, we can work out the Laplace transform of a whole family of time domain functions by a clever combination of the pairs and the properties. And even though that's not something you do that often, it allows you to become comfortable and familiar with these pairs and properties. And if you like, it's one of those questions where it's not straightforward what to do. It's what we call a game, a strategy, what combination works. Most of the questions that we've done so far are what I call plug and play. Just follow the recipe, plug in the numbers. Yes, it gets tedious, but you follow the procedure. This one is a case where you have to think exactly how to align the problem and which step goes first, second, and third. That's something in engineering you really need to be good at. Questions for which the process and how you answer the question is undefined. You have to figure out yourself how to go about answering a question. So this is a good practice exercise for real-world situations where you have to do something similar. So even though trying to work out the Laplace transform of that is not something you'll encounter as a real-world problem, the way you address this problem will teach you how you actually approach this for real problems where the solution steps are not evident. So how would you address this? Now, I'll spend a bit of time describing this, simply to get a feel for how you use the tables and become familiar with them. So what I've done is, and I hope that my system here works, I've got two versions of my notes. So this version I'm going to jump to when I want to look directly at the pairs or the properties. So let's look at this one here. What you need to do is you need to look at that before you do anything and work out which pairs are relevant here and which properties are relevant. Which one you look at first depends, and of course the pairs are not that evident if they are, if I can put it this way, subject to a property having been applied to them. What does that mean? Well, let's look at this already. Let's see what we can see. What do you see? You see a convolution? And if you're really familiar with the properties, and you would by now, since you're just following this lecture, you remember there was a convolution property. That's why you should always have the table on hot standby, because then you can see the convolution property. Don't apply it yet, just know that there is such a thing. This one here, is this a property or a pair? This is a pair. So there is a pair. So we can use a pair there. You don't have to worry about anything else. How about this one? This one looks like that, but you can tell the difference between this and the table of pairs is a shift, because you're shifting t by 2. So this is actually subject to a pair, which is this one, and a property, which is this one, because you've shifted it. So we've identified the properties. There's a convolution property in play. There's a shift property in play. And we've identified 2 pairs. How do we combine these 4 things together? Now, how you combine them, the different techniques in terms of how you combine them and in what order. Usually top-down is best. So you start off with the first thing you can do, which encompasses all of this. So the first thing is, of course, the convolution, because that groups both the left and right side. So you do a top-down and break it into that. And the way to break it down is if you generate 2 functions. So one is w, which represents that. One is y, which represents that. Reason, because you can apply the convolution property directly to this expression here. Then we look at w and y separately. W is equal to that, y is equal to that. Y is the easiest one because we know there is an existing pair that allows us to work out what the Laplace transform of this is. And the pair is, of course, this one here, which allows us to work out this. So it's 1 over s squared. And that's what we have. You can also throw in the region of convergence. Sometimes we don't ask for that. It's always good practice to remember to do that, but if you're not asked for it, don't worry, but if you are asked for it, remember to include that. How about the W? Okay, the W is a dual combination, pair and property. So the first thing we do here is this is the solution where you invent multiple auxiliary functions. So now we invent a function called V, which is in fact the one for which we can apply the pair. So this is the exponential function. And we can apply the pair from the table of pairs, and we should know by now that if you have an exponential function like that, its Laplace transform is that. And of course, that's the region of convergence. And W is equal to this shifted by 2. And now we use the properties table. And for the properties table, we include this term, e to the minus s tau. So tau in this case is 2. So that's what we have. And that's going to be 2. So putting it all together, there we go. This is the Laplace transform of W. So we got the Laplace transform of W, which is this. The Laplace transform of Y, which is this. We know that the 2 are convolved. And we know from the convolution property, convolution in the time domain is multiplication in the S domain. So that means we should be multiplying this by that. And indeed, that's what we do. Now, what can we say about the region of convergence? Real part greater than 0. Let's see if I can work that one out. Well, we have to look at all of these. That's real part greater than 0, real part greater than -3, real part greater than -3. And hence, the real part greater than 0 is the one that includes all. In the properties table, it's, I think the one that holds, it would be something like that, the intersection of the 2 between the X and the Y, and of course the individual properties of the pairs. Now, I'll leave you with a think question. We were able to figure out what the Laplace transform of this was, How about if we want the Laplace transform of this? How do we carry that out? Now, that's a question that is in one of the tutorial questions, and it's a nice question I like to ask on a test, an exam, because there's a bit of a process here, and it's, once again, it's a strategy of what you do to handle this. It's also one of those questions where you have to be careful, because most students will incorrectly apply the shift property. So it's one of those that you have to have an understanding of the mathematics as much as anything else. So have a think, what is the difference between this one here and that one there, and how do we resolve it? Something for you to think about. Okay, I think I've spent enough time on this, so I will call it a quits for now. But when we come back, I will look at literally the inverse problem of how you go from the Laplace transform back to the time domain, as I've already indicated, using the integral expression that we just briefly touched on is not something you want to do. So you will have to use the table of pairs and properties, especially the table of pairs, and a technique called, and I think you probably know about this technique from your maths, but you may like to look it up before you go to the next module, and the technique is partial fraction expansion. Okay, more about that next time.